Welcome back, everyone, to another deep dive into the OEIS.
Yes, always exciting to jump into a new sequence.
Today we're looking at A00126.
It's a fascinating one.
Yeah, definitely looks like it. I see connections to ternary numbers, Fibonacci, spirals, even binary words.
That's what I love about the OEIS. There are so many surprises.
All right, so let's break it down.
Sounds good.
What are the first few terms, and what exactly is a nonlinear binomial sum?
Okay, so the sequence starts 1, 2, 4, 8, 15, 27, 47, 80, and keeps going.
Okay, I'm already intrigued.
Now, a nonlinear binomial sum, well, binomial comes from the binomial theorem.
Right, which deals with expanding expressions like x plus y to the nth power?
Exactly. And each term in that expansion has those binomial coefficients.
Okay, remember those.
So nonlinear binomial sum just means we're combining these coefficients, but not in a way that creates a simple linear pattern.
Makes sense. So where do ternary numbers fit into all of this?
This is where it gets really interesting.
Ooh, I like it.
If you subtract 1 from any term in the sequence, that number tells you how many ternary numbers fit certain criteria.
Ternary numbers, those are numbers using base 3, right?
Yeah.
With digits 0, 1, and 2.
You got it. So these ternary numbers can't have any 0 digits. They have to have at least one 2 digit, and the sum of their digits can't be bigger than the position of that term in the sequence.
Okay, that's a bit to wrap my head around. Can we walk through an example?
Definitely. Let's take the fourth term, which is 8.
Okay.
Subtract 1, we get 7. So we're looking for ternary numbers with no zeros, at least 1, 2, and a digit sum less than or equal to 4.
Less than or equal to 4.
Got it. And if we list them out, they're exactly 7, 2, 12, 21, 22, 112, 121, and 211.
Ah, I see. They all fit the rules. But why ternary numbers? Why this connection?
It's not random, even though it might seem that way. The restrictions we put on the ternary numbers, no zeros, at least 1, 2, those actually mirror how the terms in the sequence are built up.
So they're connected in how they're constructed.
Right. They both involve combinations and choices, but with certain constraints.
That helps me see it better. So we've got this link to ternary numbers, but I also heard A00126 shows up with Fibonacci spirals.
It does, and it's super cool to visualize.
Visuals are always helpful.
Imagine building a Fibonacci spiral with squares. You start with one square, then add another of the same size next to it, then a square with side length 2, so you have a rectangle, then one with side length 3, and so on.
Following the Fibonacci sequence 1, 1, 2, 3, 5, 8, I get it.
Exactly. Now focus on the corners of the spiral where it turns.
Okay, I can picture those.
If you number the squares as you go, the position of those corner squares is given by our sequence, A0000126, 1248, and so on.
Wow, that's amazing. A sequence defined by a nonlinear binomial sum having this geometric representation.
Isn't it neat? And that's not all. A0000126 also appears when we talk about binary words.
Binary words like strings of zeros and ones.
Those are up next. These binary words are strings of zeros and ones.
Right.
And A0000126 gives us the number of these words with a certain length and a specific rule. You can't have 2 or more zeros between any 2 ones.
So like a 3101 would be okay, but a 3010 wouldn't because of those 2 zeros between the first 2 ones.
Exactly. And the number of these valid binary words for a given length, that's the matching term in A0000126.
So we've got ternary numbers, Fibonacci spirals, binary words, all tied to this sequence. It makes me wonder, is there a deeper reason for these connections, or are they just like happy coincidences?
That's a question mathematicians are always asking. Sometimes these connections point to deeper mathematical structures that we haven't fully understood yet.
So there could be more to uncover.
Definitely. Other times it might be more like a beautiful coincidence showing how elegant and interconnected math is.
I like that idea. So we've seen how A0000126 relates to all these different things, but are the concepts themselves connected? Do the ternary numbers relate to the binary words, or are they completely separate?
There might be connections. Researchers are still exploring all the possibilities.
Always more to find out.
But there are hints. One that stands out involves something called the permanent of a matrix.
Matrices. Now, how do those fit in?
Imagine a square matrix filled with zeros and ones following a specific pattern.
Okay.
In each row, the first entry is a 1.
Got it.
And in each column, the last entry is also a 1.
Right.
And any entry right next to a 1, horizontally, vertically, or diagonally, is also a 1.
So a 1 kind of creates a cluster of 1s around it.
Yes, exactly. All the other entries are zeros.
Okay, I can picture that pattern. So how does this matrix relate to our sequence?
Calculated a bit differently.
Okay, I vaguely remember permanence.
The permanent of this specific type of matrix, the n by n matrix, gives you the nth term of A0000126.
So the arrangement of 0, 0s, and 1s in the matrix somehow encodes the same information as those ternary numbers, the Fibonacci spiral positions, and the binary word counts.
It seems that way, although the exact connection isn't fully understood. It's like having different maps of the same place, each highlighting different features.
I like that analogy. So A00126 is like a bridge between these different areas of math.
It is. And speaking of bridges, is there a way to move between these different interpretations? Could knowing about the binary words help us understand the matrix better?
That's a great question.
It's an active area of research. There are hints that the pattern of zeros and ones in the matrix might reflect the restrictions on the zeros in those binary words.
So the matrix is like a visual representation of those restrictions.
Yeah, something like that. Unraveling that connection could lead to some new insights.
It's also fascinating. But maybe we should take a step back and look at some concrete ways to calculate the terms of A0000126.
Good idea. We have formulas beyond these interpretations: recurrence relations, a closed-form expression, and even a generating function.
Sounds like a lot to unpack.
Mm.
Formulas, those are always helpful.
They are. Let's start with recurrence relations. They're great for understanding how a sequence builds upon itself.
Right, so how does one term relate to the ones before it?
Exactly. So one recurrence relation connects A0000126 directly to the Fibonacci sequence.
Ooh, Fibonacci, I love those.
Any term, let's call it an, is equal to the n plus third Fibonacci number minus n plus 1.
So if I want the 10th term of A0000126, I need the 13th Fibonacci number and then subtract 11.
You got it. And there's another recurrence relation that defines a term using the 3 terms before it.
Okay, what's that one?
An is equal to twice the n1th term minus the n3th term plus 1.
So we have 2 different ways to find a term using recursion.
Right. Different tools for different situations. What about a closed form expression? Is there a way to calculate a term directly without needing any previous terms?
That would be handy.
There is, but it's a bit more complex. It involves powers of the golden ratio. 1 plus square root and 5, 2, and its conjugate, 1 square root 2, 5.
Golden ratio, always popping up.
It does. And finally, we have the generating function. It represents the whole sequence as a power series.
Generating functions are always a bit mysterious to me.
For A0000126, it's 1x plus by 3, 1 mic by 2, 1 by 2, 1 by 2.
That's quite the expression. So many formulas: recurrence relations, closed form, expression, generating function. It's amazing how one sequence can be understood in so many different ways.
It really shows the depth and interconnectedness of number theory.
And the beauty of math in general. We've gone from ternary numbers to Fibonacci spirals, from binary words to matrices and permanents.
And we've seen how these seemingly different concepts are all intertwined.
It's like we've assembled a puzzle with all these different pieces fitting together.
Exactly. And A0000126 is the picture that emerges.
As we wrap up this deep dive, what would you say is the most important takeaway for our listeners?
I think it's the realization that even something as simple as a sequence of integers can hold hidden depths and unexpected connections.
It's a reminder that math is full of surprises.
0000126 is a beautiful example of how different areas of mathematics, combinatorics, number theory, linear algebra can intersect in surprising and elegant ways.
It's a reminder that mathematics is a living, interconnected web of ideas, and there's always more to discover.
Yeah.
Well said. It's been a truly fascinating exploration.
I agree.
To our listeners, keep exploring the OEIS and the countless other mathematical wonders out there. Until next time, happy exploring.